432 Hz, the hidden language of the universe. From galactic spirals to labeled spectra, the universe shimmers with measurable oscillations. Interference ripples in a nebula reveal constructive and destructive wave patterns. Inside a meteor crystal, lattice vibrations appear as phonon bands with labeled spectra. Atoms resolve as probability clouds with annotated nuclear vibrational overlays. A 432 Hz sign reference appears as a HUD, compared with 440 Hz and nearby harmonics. Warm light reveals Pythagoras studying metallic rods and marked lengths. A monochord sliding bridge demonstrates 2:1, 3:2, and 4:3 ratios. Water bowls tremble into standing waves when rods excite their rims. Wave harmonics on strings, visualize the harmonic series under clear labels. A note clarifies. Ratios define consonants, no fixed 432 Hz standard is implied. Calibrated oscillators drive speakers. A 4 equals 432 Hz and a 4 equals 440 Hz with plus or minus 0.02 Hz stability. Oscilloscope traces show phase-stable signs with equal amplitude. Graphs compare wavelengths in air at 20 degrees Celsius. Lambda 432 is approximately equal to 0.793 meters. Lambda 440 is approximately equal to 0.782 meters. Instruments alternate. A retuned piano and sustained violin tones with FFT overlays. A subtitle notes a pitch offset of is approximately equal to 31.8 cents. Timbre depends on overtones and technique. A dark lab reveals a shallow dish on a driver with precise readouts and controls. Near resonance, symmetric standing waves form with nodal lines clearly marked. At exactly 432 Hz, the pattern matches the nearest dish mode to that frequency. At 440 Hz, a different nearby mode appears, with altered symmetry and nodes. A caption clarifies. Patterns arise from container geometry and resonant modes. A stainless vacuum chamber stands ready with laser vibrometers and microphones. At 101 kilopascals, microphones log SPL while vibrometers track diaphragm motion. As pressure drops toward 1 kilopascal, mic response falls but vibrometer remains. Calibration tones and timestamped logs confirm experimental rigor and traceability. Data panels summarize amplitude, stability, pressure range, and impedance changes. Two coupled masses exchange energy when driven near a natural frequency. Resonance emerges as amplitude spikes at the system's natural modes. A molecular lattice illustrates acoustic and optical modes by analogy. Energy transfer efficiency peaks when the drive matches a mode. Phasor relationships reveal lock-in at resonance and quick slip off it. A softly glowing brain appears with labeled EEG bands across the cortex. A caption separates the 432 Hz carrier from slower neural rhythms. Coherence maps show plausible alpha increases during calm listening. The oscilloscope tracks amplitude-modulated alpha while music plays. Data integrity is emphasized with timelines and controlled conditions. Heart and lungs glow softly while graphs of ECG and breathing scroll. Music alternates between A4 equals 432 and A4 equals 440 at constant tempo and level. Waveform overlays align to musical beats, not carrier frequency. Microvascular highlights pulse with each beat under soft blue lighting. Independent parameters are separated: tempo, SPL, and pitch standard. Earth at night glows with auroras as global standing waves are labeled. A caption clarifies these are ELF electromagnetic cavity modes, not audio. Mathematics shows why many harmonics are needed to approach 432 Hz. An ELF receiver spectrogram displays peaks at expected bands only. A concluding note separates coincidence from physical coupling. We enter a reconstructed temple where proportions shape its sound. Ray-traced paths reveal reflections and pressure nodes among columns. A choir tone glides through room modes as the response is measured. Annotations emphasize proportion and reverberation over fixed reference A. We glide across carvings as pressure maps paint harmonic nodes in color. A reconstructed archive room reveals documents charting varied historical pitch standards. A frequency timeline highlights A4 adoption as a coordination standard, not a sonic supremacy claim. Recreated radio oscillators and documents show engineering motives for consistent tuning. Psychoacoustic charts illustrate subtle pitch shift effects without privileging any reference. The conclusion board states, 440 Hz standardized tuning aided coordination across ensembles. A calibrated studio stages a string quartet for precise A-B tuning comparisons. At A4 equals 432 Hz, the quartet sustains tones while FFT peaks are labeled in real time. At A4 equals 440 Hz, identical dynamics and tempo maintain fairness for direct comparison. Overlaid waveforms and phase coherent takes demonstrate the global pitch offset. Results panels summarize. Harmonic spacing stays integer, peaks shift by 31.8 cents. A glass dish of water glows under blue light as sensors track surface wave coherence. An explanatory panel clarifies audio modulates macroscopic motion, not molecular vibrations. Phase plots align across sensors as the drive stabilizes, coherence remains high. A slow pan reveals ripples, refraction patterns, and the live coherence readout, 0.98. Final annotation states measurement conditions and cautions against overinterpretation. Portrait stations capture ultra-slow facial reactions under matched audio conditions. Micro-movements in eyelids and cheeks are measured while tempo and loudness stay constant. Metrics align to musical phrasing rather than reference frequency alone. A results pane shows within subject variability and avoids overreaching interpretations. Summary text, context, harmony, and dynamics strongly shape emotional perception. A fog-filled chamber reveals a green laser sheet that slices the air with vivid precision. At 432 Hz, labeled node spacing corresponds to lambda as approximately equal to 0.793 meters in air at 20 degrees Celsius. At 440 Hz, the grid tightens. Labels update to lambda as approximately equal to 0.782 meters with phase lock confirmed. A Schlieren-style insert visualizes pressure gradients that structure the standing field. Final panel confirms calculations, node distances, and stable environmental conditions. A precise ORI displays orbital periods with labeled frequencies far below audio. Scaling panels explain that mapping to audio requires mathematical transposition. Numeric overlays show how coincidences can occur across vast ranges. The orrery continues in calm motion, reinforcing careful interpretation. A faceted crystalline sphere hangs in dim blue-violet light, ready to synchronize. Phasor arrows sweep across facets, forming coherent interference bands. Labels clarify. Audiovisual synchronization illustrates coherence by design. Moiré patterns stabilize, revealing crisp phase alignment across facets. A faint waveform glows amid stars as the camera begins a gentle pullback. Text appears. Every atom vibrates, every star sings, maybe harmony was never lost, only retuned. The camera retreats past galaxies, leaving measured light to recede into silence. The final glimmer fades to black, the last trace of coherent motion dissolving. Title card states the film and its verifiable, method-driven mission. A lab notebook flips, listing instruments and calibration standards. A modular rig stands ready, underscoring commitment to transparent methods. The scene sets a rigorous tone. Evidence over myth, clarity over conjecture. A climate room displays temperature and humidity as baseline conditions. Overlays compute C is approximately equal to 343 meters per second and expected wavelengths at 432 and 440 Hz. Schlieren visuals show tone bursts traveling across the ruler rail. Temperature shifts demonstrate small, measurable wavelength changes. The luthier documents the baseline. Instruments at A4 equals 440 Hz under stable room conditions. Precise target set. The tuner switches to A4 equals 432 Hz, showing a 31.8 cent offset. The piano is retuned. Pins turn while the tuner confirms the new reference. The violin follows. Bridge and soundpost are checked as string tension shifts slightly. Verification passes. Spectra before and after show identical harmonic spacing, shifted globally. A virtual string displays its fundamental and neatly spaced harmonics in luminous clarity. Switching the reference from 440 to 432 slides the entire ladder slightly leftward. Beating emerges when near equal tones meet. Interference outlines the envelope. Nodes and antinodes mark fixed harmonic positions along the simulated string. A concise caption separates beat rate from brain band frequencies to avoid confusion. A double-blind listening booth is prepared under controlled, calibrated conditions. Playback levels are normalized so loudness does not bias preference. Randomized labels prevent expectation from steering the outcome. Listeners submit impressions, results show individual variability. A summary panel underscores that preference is nuanced and context-dependent. A sweep excites wood, metal, and glass. Transfer functions reveal their eigenmodes. Spikes in the plots correspond to geometry and material-defined resonances. Near 432 or 440, some modes appear by coincidence, not because of special selection. Textures shine as the sweep pauses, nodes and antinodes shimmer on surfaces. An XY oscilloscope blooms with elegant Lysage's figures in violet and silver. Pure 432 and 440 form ellipses at slightly different rotations and axes ratios. Adding harmonics creates intricate yet periodic shapes governed by phase and level. Phase alignment locks patterns, misalignment tilts and skews the geometry. The takeaway: visuals reflect signal math, not a privileged pitch standard. The violin E string is measured as reference pitch shifts from 440 Hz to 432 Hz. A clear formula links frequency, length, and linear density to string tension. Strain gauges quantify the small tension change from 440 Hz to 432 Hz. Spectrograms reveal attack transients vary chiefly with performance, not reference. A fair A/B shows pitch reference shifts while relative harmonics stay fixed. A stone hall shimmers as a choir prepares matched passages at both references. Impulse responses are captured to characterize the hall before the takes. First passage at A4 equals 432 Hz, fills the nave with smooth modal support. Second passage at A4 equals 440 Hz shows comparable room behavior with slight offset. Plots of T60 and clarity confirm space drives tone blend more than reference. Calibrated sources anchor every measurement before comparisons begin. The piston phone sets microphone sensitivity against a known sound pressure. A rubidium standard locks frequency counters for oscillator accuracy. Laser vibrometers verify diaphragm excursions at 0.8 micrometers peak. Uncertainty budgets accompany all figures shown in later scenes. Two pure tones at 432 and 440 Hz create an 8 Hz beating envelope. A spectral view reveals carriers and sidebands under AM analogy. Lysage's figures rotate slightly between the two pure tones. A caption clarifies beats as perceptual interference, not special resonance. Level-matched A/B ensures loudness does not bias the demonstration. A software synth reveals how reference A and temperament shape pitch maps. Frequency tables slide slightly as it changes, intervals remain consistent. Temperament selection changes interval color far more than reference A. A rolling spectrum confirms stable interval ratios under either reference. A concise panel summarizes: reference sets pitch, temperament sets intervals. A pristine studio reveals colored planes marking axial, tangential, and oblique room modes. A precise sweep exposes peaks and dips as the analyzer plots the room's frequency response. Step tones at A4 equals 432 and A4 equals 440 reveal similar modal behavior with slight shifts. A moving mic map shows pressure nodes and antinodes across the listening area. Treatment placement reduces peaks. The response smooths without changing the tuning reference. An inner ear model reveals the cochlear map from low to high frequencies. Critical bands illustrate how nearby tones can mask one another. A controlled A/B panel demonstrates the subtle pitch difference between 432 and 440. A masking demo shows a narrow noise band obscuring 432 while 440 remains audible, then reverses. Context matters. Melody, tempo, and dynamics shape perception more than reference alone. A macro crystal reveals standing wave interference across shimmering microfacets. Group versus phase velocities separate as dispersive bands sweep the lattice. Beating patterns emerge when two close spatial frequencies overlap. Boundary reflections set up partial standing waves and shifted nodes. A summary panel clarifies interference and dispersion without invoking mystical claims. A meadow soundscape unfolds with birds, wind, and distant bell over rolling hills. A handheld tuner samples the bell's partials, mapping natural pitch drift. A portable speaker emits 432 and 440 tones. Terrain shapes propagation differences. Spectrum overlays confirm terrain, not tuning choice, creates measured variations. The field test underscores context. Nature's spectra are broad and untuned. An animated timeline traces tuning practices from just to well to equal temperament. Keyboard animations demonstrate key colorations in well temperaments. A dial highlights varied historical reference. As across cities and centuries, animated intervals show temperament changes versus a simple reference shift. A cautionary note underscores evidence. Avoid overlinking any culture to 432. An anechoic chamber reveals a rotating loudspeaker prepared for polar plots. At 432 Hz, the polar sweep traces a near-circular pattern around the mic. At 440 Hz, directivity remains essentially the same within measurement tolerance. SPL heat maps around the room illustrate geometry-driven interference. Calibration confirms matched level and traceability before concluding. We ride along a vibrating string, entering a world of nodes and antinodes. Harmonic markers flash as the camera crosses the first few nodes. Switching reference, shifts the entire harmonic ladder slightly. Beats appear when two near equal tones cause slow amplitude swells. Integer relationships persist. Only the pitch baseline has moved. Cutaway views reveal air columns shaping tone inside trumpet and flute. Players adjust embouchure and valves or keys to hit target fundamentals. Side-by-side spectra show overtone structure governed by bore design. The camera glides through the trumpet bell, mapping reflections and loss. Players adapt intonation. Instruments do not inherently prefer a reference. A strobe reveals nodal rings and diameters on a tensioned drumhead. Tone bursts excite discrete modes determined by geometry and tension. At 432 and 440, the membrane couples to whichever mode lies nearest. Percussive spectra align broadly. Reference affects musical context, not physics. Measured data and clean visuals close the membrane mode demonstration. Algorithms estimate pitch from audio frames under controlled conditions. A pure 432 test yields a stable estimate with tight confidence bounds. A pure 440 test similarly locks, separating the two references clearly. Complex music fluctuates. Instantaneous pitch tracks vary with vibrato. Noise and jitter increase error. Robust methods report uncertainty bands. A crisp impulse triggers the hall's unique acoustic fingerprint. Microphones capture the decaying reflections across time and space. An FFT reveals the hall's spectral signature from the impulse response. Music convolved with the hall's IR blooms into lifelike depth. At both references, space colors tone, performance shapes perception. Blind labels randomize conditions to test expectation effects. Participants rate differences even when clips are identical. Swapped labels expose how naming steers perception. Results plot preference with error bars and sample sizes. Careful methods clarify subtle tuning perceptions from bias. 3 panels isolate tempo, pitch, and dynamics for fair comparison. Listeners judge calmness tracking slower beats and softer levels. Pitch reference shifts show subtler effects beside tempo changes. Timbre and orchestration dominate the sonic character. Single variable tests reveal what truly shapes perception. Bench instruments test identical tracks at both references. THD and IMD plots show negligible differences within uncertainty. Noise floors and frequency response remain functionally the same. Evidence encourages careful listening over assumptions. Measurements align with transparent, evidence-based practice. A score scrolls as pitch labels update with the reference change. MIDI notes stay fixed, only the frequency table shifts. Orchestration layers illustrate register and color, not mystique. A sidebar notes historical practicality in pitch choices. Transparent labeling clarifies what changes and what does not. A sand-dusted metal plate hums as a swept oscillator finds discrete modes. As frequency rises, sand migrates to nodal lines, sketching elegant eigenmodes. At 432 Hz, the plate shows the mode closest to that frequency documented and labeled. Retuned to 440 Hz, a nearby mode appears with a different symmetry map. A side-by-side comparison confirms geometry governs patterns, not a special frequency. A binaural head faces a speaker array in a matte blue acoustic room. HRTF curves reveal pinna-shaped filtering that defines direction and height. Clips at A4 equals 432 and A4 equals 440 render in identical spatial scenes for fairness. Spatial heatmaps show interaural cues dominating the listening impression. A quiet note, tuning choice affects pitch, while space is shaped by acoustics. An orchestra settles as the oboes arises in a luminous hall. The ensemble demonstrates passages at A4 equals 432, then at A4 equals 440. A sidebar notes many modern groups favor 442 for brightness and blend. Listeners perceive balance shifts mostly from performance nuance, not standard. The hall's soft reverb bathes the sound. Variables are carefully documented. A command console aggregates measurements from every experiment. Frequency readouts confirm 432 and 440 are precisely generated and stable. Comparative FFTs display global tuning offsets with matched timbral envelopes. Physiology panels summarize plausible trends without overstating causality. A closing grid cites calibration, environment, and methods for every scene. Historical instruments rotate as labels note diverse reference pitches. A timeline reveals overlapping standards rather than a single universal A. A sidebar explains artistic choice, select pitch for repertoire and voices. Regional dials highlight that 432 is one valid choice among many. The exhibit closes with a balanced reminder to document tuning clearly. A custom microtonal keyboard powers up, its violet LEDs mapping 19 and 24 TET layouts. The reference A changes between 432 and 440 while the scale remains microtonal. Keys trigger sustained tones. Spectral displays reveal dense but orderly partials. Switching to 24 TET, the octave divides into quarter tones. Intervals compress evenly. With A equals 432 versus 440, patterns translate horizontally. Interval geometry stays intact. A spectrogram workspace opens, ready to compare performances at two references. Short windows sharpen time. Long windows sharpen pitch controls, adjust smoothly. A 432 tuned excerpt displays clear harmonic ladders and expressive vibrato. Switching to 440 shifts bands upward. Expressive shapes remain dominant. Instantaneous frequency tracks reveal portamento arcs across both references. A studio mic captures sustained vowels while displays show formant bands. Reference A toggles, but the formants stay governed by vocal tract shaping. A side panel plots harmonic peaks under each formant for both references. Waveform and SPL remain controlled, isolating pitch reference as the variable. Two short pieces share tempo and orchestration, differing only in reference A. Live data shows audience preferences summarized without universal claims. Close-ups of score pages confirm identical notes and phrasing across versions. A final panel invites reflection. Preference is personal, method makes it clear. A concise board lists verified points from the documentary's experiments. 432 and 440 differ by 31.8 cents. Both function as workable references. Resonance occurs at system eigenfrequencies, coincidences are expected. Perception reflects tempo, dynamics, room, and performance more than reference. Historical pitch varied. Choose references artistically in document settings. Set your project reference and confirm devices align before any recording. Retune instruments methodically while keeping other variables constant. Measure the room response and position mics for reliable comparisons. Normalize loudness to LUFS targets so A, B judgments remain fair. Document settings reference, temperature, and takes for reproducibility. Prepare a quiet space and match volumes before any comparison. Use blind toggles to reduce expectation bias while listening. Take short breaks to prevent fatigue and keep judgments clear. Write observations precisely describe timbre, not assumptions. Save results and share methods so others can replicate easily. Revel in materials. The craft behind sound is visible in detail. Hammer felt and wire mechanics etched at cinematic clarity. Bow hair and rosin, the interface of friction and tone. Mesh and magnets, transducers rendered with faithful realism. A gentle 432 reference guides the edit as textures breathe. Show sources, methods, and limits invite verification, not myth. Preferences or valid claims require data and context. Invite the audience to try controlled comparisons at home. Clarity and integrity make the music more meaningful. Credits drift across a measured cosmos of gentle light. A precise counter glows, then settles on its final reading. The waveform fades as the universe returns to stillness. Silence holds, the last silver ember dims to black.